Okay, so as I linked in the comments, again, because the chapter I'm going to be covering today is also very, very focused on graphical representations, and since I'm not going to reproduce those, since that would waste a ton of time, I'm going to refer to those figures in the notes. So you should read along as I'm doing this to have any idea of what I'm actually talking about. So, the last few chapters have been basically since the singular value decomposition has been introduced, we have used it in a variety of ways. So, starting, I think chapter 9 is when it was introduced. So the last few chapters have been nothing but singular value decomposition applications, and this next chapter is going to be no different. So chapter 12 is character recognition. So the last thing we did, so chapter 11 was image compression, which used the singular value decomposition to essentially see how much of the data used in storing an image was actually necessary to have a good quality image, and we could compute these things using all the quantities we define from singular value decomposition. So the quantities we described like total variance or total variance proportion of the vectors we kept compared to the whole matrix of data. Those things became measures of image quality, right? When we moved to thinking of image compression and being able to toss out some of our data and still retain, a decent picture. So in this way, it might not surprise you that we can also use singular value decomposition to talk about character recognition. That is, to recognize a character that is maybe not ideally displayed, right? So think of a character, say, so one of the first couple of examples we're going to talk about is the letter X or the letter O. So you have an idea, of course, of what those things might look like properly displayed. But of course, if I were to take that X or O and blur them a little bit, maybe if you're thinking of a way of algorithmically, recognizing some character, you might see how some difficulties arise out of trying to recognize a slightly blurry or fuzzy X or O. So anyway, moving on to the first actual page of the chapter, which is on page 3. So the example they give are these 3x3 grids of X's or O's. So I can actually draw these. These aren't too bad. So I have a 3x3 grid, and my grid that is shaded in this way, where the shading I'm doing here indicates a solid black square, and not shading a square indicates that it is solid white. So there is what we call an X, right? So as far as 3x3 grids go, that looks close enough to an X for us. Similarly, an O in this way would be exactly what you think it is. So I have actually shaded all of these boxes around the edges. So here's my O. Okay, so here's O. All right. Now, there's two more I can consider. So maybe I'll put them to the side here. So one is there's no grid lines on the actual picture in this chapter, so I added those in to make sure my drawing wasn't completely disastrous. So here's the first one, and this is an almost X, right? So this is an almost X. Okay. So maybe you don't consider that as looking like an X, but viewed in the way that we're encoding these X's and O's by whether or not I've shaded one of these squares, I'm only one square off here, right? So I'm a single square off from this thing being a proper X, if I've defined this to be a proper X. And then there's an almost O that I'll put here. And my almost O is going to similarly be, I shade everything except that upper left corner. Okay, so here is my almost O. Okay. Okay. So I have these four characters. Here's my baseline X, my proper O, and then I have these two that are not quite those, but in some sense they're close enough. Okay, so we are saying that they are acceptable. Now, the idea here is using the same scheme for storing color data pixel by pixel for these things. The way that I would do this is I would store these in a 3x3 matrix. So if 0 is black and 1 is white, then this as a matrix would be 0, 1, 0, 1, 0, 1, and 0, 1, 0. Right? And this matrix for O would be zeros everywhere with a 1 in the middle. Okay. Similarly, this matrix is going to be, so this is 1, 1, 0, 1, 0, 1, and 0, 1, 0. So this is almost this matrix, except there, instead of having a 0 here, there's a 1 here. And lastly, this almost O only has 1s there and 0s everywhere else. Okay. All right, so there's my matrices. Now, the idea is to label these in some way. The first few computations I'm going to do with these, I could actually leave them in this form, but it turns out that more conveniently, what I'm going to want to do is unroll these matrices. So I want to unroll these. So if I'm calling this, I'm going to call this X, and I'm going to call this thing X question mark. So it's almost X. Or sorry, that's not. I was reading the notes directly. This is going to be O. So this is my O, not to be confused with the 0 vector or 0 matrix. Here's my almost X, so this is X question mark. And here's my almost O, so this is O question mark. Okay. Now I used vector notation here, even though these are matrices, and the reason for that is I'm going to unroll these as vectors. So I want to unroll these matrices to be vectors. Okay. That's not too crazy. I do this by putting each column below the previous one. So to unroll, I put each column below the previous one. Okay, so to unroll, I put each column below the previous one, and so I get vectors. So my vector X that is associated to the letter X would be, let's just go back here for a second. So first column is 0, 1, 0. All right, so first column 0, 1, 0, then 1, 0, 1, and then 0, 1, 0 again. Okay, so that's X. And then I do the same thing for all the others. So my questionable X is then 1, 1, 0, 1, 0, 1, 0, 1, 0. So that's my questionable X. My O has zeros everywhere except this middle slot. So this is 0, 0, 0, 0, 1, 0, 0, 0, 0. Okay. And lastly, my questionable O is 1, 0, 0, 0, 1, 0, 0, 0, 0. Okay. And once we've put them in vector form, I can compute the distances between these things. So note that the distance between X and questionable X is, well, they only differ by a 1 here, right? Every single slot here is the same except the first two, and those differ by a 1. So the distance between those two things is 1. It turns out that the distance from x to questionable O is 2.4495. The distance from O to questionable O is also 1 for the same reason. They only differ in that first slot. And then the distance from O to questionable X is also 2.4495. So a couple of things to note from this quick computation. Well, just from reading off these distances, intuitively, what is this saying? This is saying that questionable X is closer to X than it is to O, and vice versa, right? So that the X's, the proposed X's, the actual X and my questionable X, they're closer to each other, just like the O's are closer to each other than they are to the other letter. Okay. So that's not too surprising. That was kind of the point of this example. And so the question is, how do I recognize a particular character? Okay. So given an unknown character, how do I recognize it? Okay. Well, the very simple idea is to compare its distance to known letters or characters. I don't want to confuse you. I'll try to just use characters here because really that's what I'm interested in, not necessarily letters. But the idea is to compare its distance to known letters and characters and have some acceptable notion of how close it is to being a known character. So that's the basic idea. Okay. So in the online notes, he says here next, so really simplistically, given an unknown character, you could simply ask how far it is from the X that you're given or from the O that we listed, and then decide. So then he gives an example that is like our O, except one more black square has been removed. So it almost looks like a J or something. So he gives an example of a character. This is at the bottom of page 4. It says if we convert this to a matrix and then unroll it to a vector, you get some vector u, and then you find that when you compute the distance, comparing it with x and o, you get that it has a greater distance to x than it does to o, and so we call it an O. Okay. Now, maybe I'll write that. So in the example, on page 4, consider the character whose matrix is 1 1 0 0 1 0 0 0 0. Okay, so this gets unrolled to a vector I'll call u. So again, to unroll a matrix to a vector, you just go column by column. So 1 0 0 1 1 0 0 0 0. And then you compute the distance from this vector to our x. It turns out that's 2.2361, and the distance of this vector to our O, which it turns out is 1.4142. Okay, so U is closer to O, thus it is an O. Now you might already spot what it is that's an issue here. One, I am assuming essentially that I have a catalog of characters, right, that I'm comparing to, right? That's the idea. So I have some list of known characters that I'm comparing to. Now, if my list isn't big enough, then you can see how I take a character that is clearly like pretty different from the existing list of characters, but because I have to pick something it's closest to, I make a choice, but it's not actually that character, right? So maybe this thing would be closer to a J or would be closer to a U, right? Especially. And so, but U is not a letter that's included in my X's and O's, right? So I have a list of characters that is X and O, so I'm only comparing it to those two things. So of course the idea is I want to have a robust catalog, right? You might say, oh, well, I want to have as many characters as possible to compare to. But there's issues with that as well. So that's the first issue. Another issue with this process is shown right there on the same page, on page 5, is that shifting a character slightly, so just shifting a character slightly in a larger grid can create a huge distance, even though apparently just looking at them using your instinct or your intuition, those characters are very, very similar. So, for instance, at the bottom of page 5 shows so I should say bottom of page 5 shows several issues with this. So, the first thing, shifting a character slightly in a larger grid creates a huge distance. So, for example, the following two X's are stored in a 16 by 16 grid. They are distanced 7.7 apart when they are converted into vectors because one is shifted from the other in a way that misaligns the values. But if you just look at them, right, if you just look at those X's, they look very similar to us, right? But to computer that is trying to recognize that character, they look like they're not that similar. They look like they're far apart. So we want to mollify that. We want to fix issues like that. I don't want to be stuck where I'm tossing out characters that I shouldn't, that I should be considering very similar or very close. Instead, I'm considering them far away. So that's no good. A second issue, rotating a character slightly does the same. So if you take a character and rotate it just a little bit, the apparent distance would be huge, even though the actual distance wouldn't be. So if you take one of those X's and you slightly rotate it just a little bit, the distance is actually a lot bigger than you think it would be. And that's no good either. And of course, there are many different versions of any character. So this is, another problem of, think about it just for a letter, right? You have a letter A. You want to recognize it as A, but there's A's, everybody's handwriting's slightly different. So there's different forms of A's, and there's like a script A. There's cursive A, of course. I won't get into that. But the idea is that in general, a character can have many different versions. And so the question becomes like, how do I build my list in such a way that I can have several apparently different looking characters that I'm calling the same character? Anyway, so let's see how this is going to work. So then, the idea, so this is next section, developing a robust SVD method. So what is said here is we'd really like to ask more generally what a particular character looks like. So in other words, what are the mean features and what are the more minor features and so on. Okay, and so right there, next, the essentials of a character lists 4 examples of pseudo X's, right? So sort of X's. So there's 4 examples there where they're not quite the X I began with at the beginning, and these are in grayscale as well. So now I've switched from just using ones and zeros, so I'm in grayscale where I'm using values between 1 and 0 here to indicate shades of gray. And so 2 of these X's involve shades of gray here. Okay, so then how does this work? So I take these vectors or I take these matrices associated to these characters, and I unroll them as vectors, and then I stick all of those vectors into a matrix M. Okay, so I stick all those vectors into a matrix M, and I find its SVD. So you see here at the bottom of page 6, there's matrix. Each column of M is one of these unrolled vectors coming from the characters. I look at its SVD. If I find its SVD, you see there it is. It's a very long, nasty looking thing. So there's U, sigma, V is omitted because we're not going to use it at all. And it's noted that since each column of M represents some variation of the character X, the vector U sub 1, that is the first column of U in the SVD, becomes the most important building block for all those columns, right? It's the one that contains the most variance, right? So meaning for all those X's. In other words, that single column accounts for most of the variation in all the variations on the character X. Okay, so subsequent columns are less relevant. That doesn't mean we're not going to include them in some way, so I'll talk about that in a second. So in fact, it is noted if we take the appropriate multiple of U sub 1, such that the values are scaled between 0 and 1, we get the following. So going from the column vector U sub 1 and rolling it back up into a matrix and looking at what that matrix looks like, you see what you get. Right? You see what you get at the top of page 8. You get something that looks a lot like our character X, right? So this is nice because we didn't actually, the character X itself was not one of the 4, right? So the original X that we used at the beginning of this lecture was not actually one of the 4 images that went into the matrix M that we found the SVD of here. So each of those 4 was different from X somehow, and you see that in looking at all of them, this kind of encapsulates what the mean image, or not image, but like the mean properties or the essential properties of what we're calling X is, right? Even though our letter X didn't show up in that list, right? So this is pretty nice. So this is very close to what we visually accept as an X. And of course, as it's mentioned, you might not only want to consider the first column of U. So if you were also to take U2 into account, it suggests that an X is mostly U1 with a bit of U2 thrown in. Okay, so perhaps when we're thinking about the building blocks for an X, we might use both U1 and U2, and we'll discuss how many of the U sub i's that we'll use here in a little bit. Okay, so this gives us an idea of how we might build like the essential properties of a character that we're wanting to recognize. So continuing the above example, suppose now we had another character and we wish to ask if we think it's an X. So now we want to take some other character and compare it to this X to see whether we think it's close enough to be called an X. So it says we could suggest that if a non-zero character can be built out of U1 and U2, then it's definitely an X. So for a character we're testing, it's almost certainly the case that we cannot build it exactly out of U1 and U2. So we ask instead if we can almost build this character out of U1 and U2. You see what is happening here in terms of the linear algebra, though. So asking if you can build a character out of two vectors is asking whether or not its unrolled vector is a linear combination of the two vectors in question. So this is asking whether or not this unrolled vector lies in the span of U1 and U2. And of course, typically that's not going to be the case. So then the question becomes, well, how close can I get it? What's the closest I can get it to this? And you should already know the answer to this because, of course, this is what we did. We did a version of this when we talked about least square solutions and when we talked about what orthogonal projection does. So the idea was that we are looking for a closest point, right? A closest vector to the vector I started with that does lie in the span of those two vectors. Okay, so a nice way to ask this in linear algebra would be to put this new character in a vector x and ask how far it is from the subspace spanned by u1 and u2. If it's not far, then it's almost an x. And if it is far, then it's probably not an x. There's a nice picture drawn at the top of page 9 that shows exactly this process of orthogonal projection onto the span of those two vectors. And of course, there's a note here that if all ideal x's are not exactly the subspace spanned by u1 and u2, but we're saying that it's close enough. It's not really going to change how we're doing stuff. So in other words, the distance from x question mark this vector, I don't know whether or not it's an x, to the subspace can be thought of as a measurement of the x-ishness of x. Or of x question mark, right? Of the unknown x. In other words, the distance from x question mark to this subspace can be thought of as a measure. That was exactly what I just said. Since the vectors u1 and u2 form an orthonormal basis for the subspace they span, calculating this distance is easy. In fact, as I said, this is just the distance from x to the orthogonal projection of this thing onto the span. So if I want to compute the distance from a vector x, it's this unrolled vector, to the span of vectors u1 and u2, the way to do this, right, the point that is closest to my point x, thought of in abstract vector space, is the distance from x to the projection of x onto the span of the two vectors u1 and u2. So I think of the distance between x and its orthogonal projection here. So in this particular example, so this is 0.6340 in this particular example. Okay. Which maybe you say is close enough. Of course, it's important to remember that distance is relative in terms of closeness, meaning what I mean by that is if you have a list of characters, then you can't just look at this distance and say, yeah, that's close enough, that's probably an x, because it could be even closer to some other character in your list, and in that case it would be recognized as that character, not this one. So that's what I mean by distance is relative here. Okay. So it says, on the other hand, if we take our actual proper original O, we find that the distance between O and this thing is, so the distance between O and the span of U1 and U2 turns out to be in the same way. So this is this is O minus, or sorry, the distance between O and its projection onto this span. And it turns out that this is 0.9790. Again, just looking at that number on its own doesn't tell you anything. All I can say here, though, is that, well, O is further away from this subspace spanned by U1 and U2 than this X is. Okay, that's the idea. Okay. All right. So, what is the general idea here? So, general summary. Okay. So, 1, construct a basis called a character basis for every character in our alphabet. And then for any unknown character, examine how close it is to the subspace, or the subspace is spanned by each character basis. And pick the one it's closest to. Now, I wrote this as 1, but really this is the ultimate goal. Okay, so this is the ultimate goal, is to do this. Okay. Now, this splits into parts. So, 1, the idea here is for any given character, alpha, we take some number n of representative versions of alpha, just like we did for x earlier, and construct the matrix for each. Secondly, we unroll each of these matrices as vectors. Call them alpha sub 1, alpha sub 2 bar, and alpha sub n bar. Okay. 3. Or I should say first, before I say find, put these into a matrix M and find its SVD. i.e., M is the matrix whose column vectors are these, I shouldn't have put a comma there, whose column vectors are these unrolled vectors coming from these matrices. And we want to find the SVD. U sigma V transpose. Okay. Continuing. So fourth step, from the resulting U, choose a reasonable collection of vectors as determined by the singular values. Okay. Okay. So say we choose K of them. So U sub 1 through U sub K. These form my character basis. Okay, so these form my character basis for alpha. Okay. Put these into a matrix called the character basis matrix for alpha. So you can call that B of alpha. So this is the matrix whose columns are these character basis vectors. And this is just a nice way of encoding all of that. So this basis spans the column space of this matrix. Which I should say, which is called the character subspace. For alpha. Okay. Thus, so this is the last step, step 5. Then for an unknown character, say beta, we could put it in a vector x. So say if this is an unknown character beta, unroll it into the vector x and compute its distance to the character subspace for alpha. Of course, that distance is the distance from x to its orthogonal projection onto the column space of this character matrix. And we call this the distance from beta to alpha. Okay. Okay. So, as is mentioned later, there is a shortcut for this. Normally you would have to compute this. This would be slightly nastier, but thankfully our character matrix is actually, it consists of these orthonormal vectors u, right? Because U is orthonormal by the properties of the SVD. So it turns out this is actually slightly easier than it looks. So 6, there is a shortcut available to us since U is orthogonal, which means that the columns of the character matrix B are orthonormal. So namely, you can see that the projection onto the column space of this character matrix of X can be computed in a nice way, which is character matrix times character matrix transpose times X. So the distance from our unknown character beta to alpha is the distance between X and this expression involving the character basis matrix. And that's what you need to know. So if we start the process with an entire collection of characters, then an unknown character can be compared against each of them in turn. Then you can evaluate which it's closest to. So last step, we do this for each character in our list to see which it is closest to. All right, so it says more accurately, we're taking each character basis for our known characters and seeing how close we can get to the unknown character using each character basis. The character basis that does the best job is the one that we choose. So there's a visualization at the bottom of page 11 of this happening, which is nice because it's showing basically its distance between two different character subspaces. So subspaces for one character and for another. So it says, in reality, there are many more subspaces. The dimension of those subspaces are higher, and the dimension of the spaces, they're in is also higher, but it's nice to see them like this. So for example, if we had 26 characters, each using a 16 by 16 resolution, and if we use 3 columns of each U, then we would have 26, one per character, 3-dimensional subspaces of the 256 dimensional real numbers, okay, because that's 256 pixels. It's 16 by 16. Okay, and so here's a nice overview of some intuitive things to keep track of. So it says in the previous subsection we had to make 2 choices. One is the number of sample digits to use and the number of singular values to preserve. So it's worth looking at this a little bit more. So first, how many representative versions of a character should we take? As I said at the very beginning of class, you might initially say, whoa, why don't I just take as many as possible, right? Why don't I have like the biggest possible, the biggest possible collection of these representative versions so that I get like the most accurate, the most authoritative version of this character. So how many representative versions of a character should we take? It may be tempting to take as many as possible. And as long as we don't take too many outliers, weird or esoteric versions, then that's usually fine. If we use too many varied versions, then the SVD gets confused about what's important in terms of variance. So this is just saying don't take too many crazy versions, because if you take, say, a bunch of versions of X that have, like squiggly ends on them, then when you take the SVD of those things, when you're actually trying to form, what it is that's essential, when you find the SVD, what is going to be encapsulated is going to be features of the letter that you don't actually consider important, right? So maybe for you, what defines an X has nothing to do with whether the ends are squiggly or not. So second, how many singular values should you preserve when you construct a character basis and character basis matrix? So again, it may be tempting to take more singular values, but in reality, this starts to cause problems. So why is this? So if our collection of characters is m by n, meaning we have n versions with m pixels each, then our U will be m by m, right? Use a square matrix. As we take more and more non-singular or non-zero singular values, the character basis starts to span more and more of Rm, As we do so, when we test a new character D, the distance between D and the span of B of A, so the column space, starts to decrease. Consequently, it becomes harder to compare a new character to a set of established characters. Okay, so the thing is that you're making your distance smaller by taking more singular values necessarily, which is bad because you're making it seem like it's closer than it is. Intuitively, what's happening is if we account for enough variation to draw every alpha, then we have so many character basis vectors in A that every character, not just alpha, can potentially be built from one of those character basis vectors. Consequently, every character, not just alpha, begins to look like an alpha. Okay, so figuring out how many singular values to preserve really comes down to testing and seeing what actually works best when tested in the real world and double check by another approach, such as a human. Right, so think of like CAPTCHA, right? So the idea here is that if you take too many, like what is it that's going on here intuitively? Intuitively, the idea is that I may begin with a character alpha that very much looks like an alpha, but if I start including all kinds of different versions of alphas, and maybe this one has a tiny tail, this, then what happens is that letters or characters that I don't intend to be calling close to alpha, if I call this an alpha, then some other letter that I would not think of as an alpha typically could possibly be thought of as being almost an alpha, right? Or being able to be made up by some combination of alphas. Okay, so this is the idea behind why taking more and more singular values is not necessarily a good thing. Okay, and so this summary has gone through yet again. So there's a nice example here. I'll quickly go over. So example on page 13 is really nice. So page 13 has a really nice example of all of these things. So you should have a look at that. I'm going to go over it quickly right now. So suppose we wanted to do simple character recognition on the digits 0 through 9. We decide to use 16 by 16 resolution, and we decide to preserve k equals 3 columns of u. Okay, so you're preserving u1, u2, and u3. So first we would need to get some samples of each digit. So here are 8 different versions of the number 7 at a resolution 16 by 16. Okay, so you see there's 8 different versions of 7. Okay, convert each of those into a matrix, then unroll each to a vector. That's 256 entries because it's 16 by 16. And then put them all in a matrix, which is a 256 by 8 matrix because there's 8 versions of them. Each of them have 256 entries in the unrolled vectors. From the corresponding U, we take the first k equals 3 vectors and construct the character basis matrix. So B of 7 in this case is U1, U2, and U3. This is a 256 by 3 matrix, so it wasn't explicitly written out here. But you have to repeat this for all the digits 0, 1, 2, 3, 4, 5, 6, 8, and 9 to get a basis matrix for every single one of those. And then given a digit that you'd like to identify, you'd unroll it to a vector and then check. So the distance from x to 0 would be the distance from x to b of 0 transpose times x. The distance from x to 7, for instance. So the singular values in question are listed out here. And so the first singular value captures most of the variance. First singular value is 37.6. So the next one is like 6, I think. And so looking at this example of what they get, this is done on page 15. The representative of 7, you'll see, is very close to a 7. It's like, yeah, there's some noise around the edges. You can tell that from some of the more slanted 7s, but what you get is very representative of a 7. Okay, so if you understand the summary that I wrote out, then you essentially know how to do these problems. The MATLAB here is really no more complicated than any of the MATLAB stuff that you did for any SVD stuff. So it's the same process. This unrolling bit can be done with reshaping. So you can use MATLAB reshape command to unroll the vectors. So that's the idea. So MATLAB reshape unrolls the vectors. So reshape unrolls, unrolls matrices. You can also use reshape to roll them back up too. So anyway, so that gives you a good understanding of, or a good solid basis, no pun intended, for what to expect for these types of questions. So as I mentioned previously, I'm going to post some problem sets later, and you'll have until May 20th to do them. So May 20th is the date of our what was going to be our original final exam. That will be when your take-home final exam is due, and I'll post it about 5 days before that. So I'll post it like May 15th or so. Anyway, so that's the plan going forward. I will see you all on Tuesday.